Okay, so welcome everyone for the afternoon section of talks. So now we're going to have the second lecture of Professor Arakawa on 4G 2D, correspondence of VOA theory.
Thank you very much. Today I'd like to start with some digression. There's several ways to construct VOAs, new VOAs from known VOAs. So Terry talked about taking orbifold and extensions. So this is in Terry's talk. And there's also construction called Corset Construction. Which goes as follows. So if you have a vertex algebra, and you have some vertex subalgebra, you consider the all elements whose Fourier modes commutes with Fourier modes of elements of U, U and MA. So this you find that has a natural, this space inherits vertex algebra structure from V. And so actually this is the same as certain invariant subspace. So this is the same as element which is killed by the action of UN for any elements of U and N for non-negative N. So this is because we have the following commutation relation, A, G, B. So if B is killed by all positive J, then B commutes with A. And you can find the opposite is true. And Corset is following. So let's consider affine vertex algebra. So you have so I think I regard G as a subspace of this vertex algebra by sending X to XT inverse applied to the vacuum vector. Then we can consider following vertex algebra homomorphism. So this is a tensor product of vertex algebra. So this is naturally vertex algebra. And you just send element of G to the diagonal element. So you consider diagonal action. And this is easy to see that it's an embedding. So you can consider commutant, coset of this vertex algebra. So this is so this is a vertex algebra called diagonal coset. And from the fact that this is generated by elements of G, actually this space is the same as a subspace that are invariant under the action of diagonal action of positive part of the affine Katsumudi algebra. So this is certainly contained in here by this description, but it actually coincides. So this kind of space is called diagonal coset. And so you can replace, for example, Vki G to its simple cosine for several choice of K. And you can also consider a corresponding coset vertex algebra. And in Nakajima's talk, so he conjecturally described equivariant homology of instanton moduli space of L singularity as a certain space associated with affine representation of affine Katsumudi. So it looked like this. So it's a tensor product of L. So this is some irreducible highest representation of highest weight lambda with level L, where L is this integer L, and tensor with some Vama module, some parameter, mu. And he considered the invariant subspace with respect to the upper Borel subalgebra of the affine Katsumudi. And if you look at this, so this is an integral representation of affine Katsumudi algebra. So LG acts here. And this is a generic representation. He considers more a universal one. So he thinks mu as a function on the parameter equivariant parameter. But anyway, this action, so this is level K, action of VKG on here. And because if you consider diagonal coset, then any elements commute with the action of G hat, diagonal action here. So this vertex algebra naturally acts on this space. So in this way, he explained that this coset VOA naturally appears in the context of AGT correspondence. And indeed, when L equals to 1, one can show that the this coset vertex algebra is isomorphic to principal double algebra of some parameter. So for ADE. So no, it's not simple cosine because I'm not taking simple cosine here. So this is a universal one, yeah. So this from this description you recover the not usual statement for the AGT that double algebra acts on the homology space of instanton moduli space. But he was explaining more general setting when L is equal or greater than 2. Then you get something which have level here greater than 1. Then we don't know anything about this coset vertex algebra. So, so description, so very little is known about this VOA. So when L equals to 1, it's isomorphic to the algebra, but we don't know how to describe. So it's an open question to describe this VOA. And another construction is screening. So this is also mentioned in both of talks of Sergei and Nakajima-san. So this is screening. So this idea is quite simple. So you pick some element, and you consider a kernel of a zero mode of this action. Then if you look at this commutation duration when m equals to 0, because then you find that A0 Bn is just A0 of B and N. From this description, you find that this is a vertex algebra. And the most famous construction is in the case of Virasoro. So you can define Virasoro as a kernel of some screening operator called screening. This is Heisenberg, sub-algebra of Heisenberg. So this is some screening. So in such a way that this realized Virasoro algebra is the same as Feigen-Fuchs free field realization. But this is for generic parameter. For generic parameter. And at some special value of parameter, this kernel is becomes strictly larger than the Virasoro algebra. And this is what Sergei was calling a singlet algebra. So this simple construction constructs many interesting vertex algebra. And so you can modify this construction of screening as follows. It's called a Vyacheslav construction. So you do the same, but this time you assume that V is a vertex superalgebra. Yeah?
So it says special values, as in several special values.
Infinitely many special values. Yeah.
And singlet algebra as in one singlet algebra.
No, it's a family.
Okay.
It depends on,
The
yeah.
family depends on the value, and we understand the singlet algebra according to the value.
Yeah. It depends on the integer, and the integer. It usually called BP.
So I know how to construct a singlet algebra in terms of a presentation, and so you're saying that it coincides in terms of
Right. Yeah. So this time you assume this V is a vertex superalgebra. And you pick some element which is odd. And you assume that the square of this zero mode is 0. Then again, you have a kernel, which is a vertex subalgebra. And then, because of this condition, image is contained in the kernel. And you find that this is ideal in the vertex algebra sense. So you get a new VOA, new VOA, a vertex algebra, by considering the quotient of kernel by image. And this is called BRST construction. So usually you assume that this is G-graded. So if you want to talk about cohomology, you need some cohomological grading. And you assume that Q has a degree 1 or minus 1. And then this is indeed cohomology in the standard sense. And so point here is that so this BRST, so I will be using BRST construction a lot because can define, can upgrade, can how to say, can construct BRST cohomology of vertex algebra in this sense by maybe often can construct BRST cohomology by upgrading the classical BRST cohomology that is studied by Constant and Sternberg some time ago. So what they did is they gave some algebraic construction of Hamiltonian reduction. So they described function on the reduced Poisson manifold as a BRST cohomology of original function of the Poisson manifold. So in this situation, BRST cohomology construction for vertex algebra is often compatible with the associated variety. So I'll explain what I mean by this in a minute, but maybe not today, but maybe tomorrow. So I don't know how associated variety behaves by other construction, but somehow BRST construction is most appropriate for associated variety approach. Okay, so my digression is over. Any question? So let's go back to what we were discussing. So we were discussing the 4D, 2D correspondence. So we have some remarkable map which sends for this theory to US theories, which makes this diagram commutative. This character. And also, conjecturally, it makes it possible to describe the Higgs branches using vertex operator algebra. So this is Higgs branch. And this is associated variety. And this commutativity is a beam-Russelli conjecture. But I have to say, beam Russelli conjecture is a physical conjecture, not mathematical conjecture. So it's not a mathematical statement because because for the n equals to 2 superconformal field theory are not mathematically defined. So if you start with undefined object, you cannot really state mathematical statement. So this is a problem, but there are cases when we can really make this statement mathematical. So this is a topic I want to explain today and tomorrow. And it's called, there's some special for this theory, which make the statement in which we can make this beam-Russelli conjecture mathematical. So it's a case, a theory of, it's called the theory of, so you have a big family of 4D n equals to supercommon field theory. And here we have some big family for the theory called a theory of classes, where S stands for 6. So it comes from 6-dimensional theory, even higher than 4. So this is a theory Nakajima-san was talking about in the beginning. So you consider 6-dimensional theory on R4 times some Riemann surface. So then you fix this Riemann surface, you get some 4-dimensional theory. And so this Riemann surface is usually punctured. So the resulting 4D theory has parameter, has this punctured Riemann surface as parameter. And it also has a semi-simple group as parameter. It's called a flavor symmetry group. Or a gauge group. So anyway, we have some family of for this theory, which is parameterized by semi-simple group and punctured Riemann surface. And for this class of for this theory, Moreau and Tachikawa gave a mathematical definition or description of Higgs branches. So you cannot define for this theory in mathematically, but you can still define Higgs branches. That's what they did. But up to a conjecture, up to a mathematical conjecture, but this conjecture was proved by Ginzburg Kazdan. And Braverman, Finkelberg, Nakajima. So you have nice mathematical definition of Higgs branches for classes theory. So let me describe these Higgs branches. So one of the statements of Moreau Tachikawa was it's enough to describe or determine Higgs branch for genus 0 Riemann surfaces. If you know Higgs branches for genus 0 surfaces, you can glue them to get a higher genus, Higgs branches for the higher genus. So I just explained the genus 0 case. So I want to describe a Higgs branch for the P1 with some punctures, let's say R punctures. And so let me denote this MT, Moreau Tachikawa GR, or M. I just don't write G if obvious. So let me describe this MTR, which I call Moreau Tachikawa variety. So let a GG be a semi-simple group. Then statement is that there exist a unique family a family of affine Poisson varieties such that, so first for, so each of this is irreducible and reduced. And so there exists a Hamiltonian action of R copy of G on this variety, Poisson variety. So we have the momentum up for each action of copy of G where G is of course the algebra of with respect to the ith action of G is flat for any I. And there are some initial conditions. So MT2, so MT2 has to have two commuting action of two commuting Hamiltonian action of G. The simplest example of such symplectic variety is cotangent band to G, and that's what it is. So you have a left action and right action on here of G on here, and MT1 is has only one action of G, and it's described by product of G and affine space called constant Schrodinger's slice. So if plus GE is the constant Schrodinger's slice. So we take E and F. So this is a regular SL2 triple. And you consider a centralizer of E and shift by F. So this, so in type for when G equals to in type A, then S is something like 1 here and 0 here, and some. So this x1. So this same, yeah, something like it. Minus 1 maybe, something like this. And there's another condition called associativity. So if you consider product of MTR and MTS, so there's an R commuting action of G here and S commuting action of G here, and you pick one action from here and you pick one action from here, and then consider a symplectic reduction. then this is isomorphic to Moreau-Chiral variety for R plus S minus 2. So it's often described as, so this representation represents what MTR for R points and S points. You can glue 2 points and get the Moreau-Chiral variety for the rest of the points. And moreover, MTR is normal of finite type of a dimension R times dimension of G minus R minus 2 rank of G. And the restriction, so this is in general a singular variety. And the restriction of Poisson structure on the open set mu I inverse regular. So this is a set of regular elements in G which form an open set in G star. Gives a structure of smooth symplectic variety. So we can call it a symplectic variety. So this is a statement, and let me make some words for the statement. So I think I can erase here. So first for so I'd like to explain why this has so this is clearly smooth symplectic manifold. And I want to explain why this is symplectic. So let N be the upper triangular matrices, upper triangular subgroup of G, maximal unipotent subgroup of G. Then constant showed that we have a isomorphism of affine varieties. So if you consider the action of this group, you get some element in G or G star, and you find this sits inside F plus upper Borel subalgebra, which sits inside G and G star. So this is the isomorphism of affine varieties. So this implies that this product can be described as this. So this is a vector bundle over G over N. And if there's no F, this is the usual cotangent bundle to G over N. So in which case, it's naturally a symplectic structure. And this is a little bit shifted, but still locally isomorphic to cotangent bundle. And it's called twisted cotangent bundle to G over N. So in particular, it has a symplectic structure. And I said Moore Tachikawa gave a mathematical definition up to a conjecture, but this conjecture was the existence of this family of so this was a conjecture of Moore Tachikawa. So this associativity condition is very important. So let's have a look at this condition. So, for example, associativity, let's put S equal to 3. Then what we get is MT R times MT 3, and if you do symplectic reduction, you get MT R plus 1. And we are given MT1 and MT2. So this means that if you know MT3, we know everything. So this determines everything. So we just have to write MT3. Now, next, let's look at this associativity condition for S equals to 2. Then it says MT R times MT2, which is cotangent bundle to G. And if you do symplectic reduction, you get MTR. So this reduction doesn't change MTR. So this is what it says. So because cotangent bundle is a very easy, simple manifold, we should be able to check this isomorphism. So let's try to check. So cotangent bundle to G is just a G times G star. And the moment map is just a projection to G star. So this is moment map for cotangent map. It depends on which action you take, but you can think this as a moment map. So let's X to be arbitrary Hamiltonian G variety and consider symplectic reduction with respect to the diagonal action of G. So X has some moment map. Then the level set is the pair such that the image of moment mat of X is the same as Y. So this is a level set, and you divide by the diagonal action of G. And because y is completely determined by x. This is the same as x times g divided by the action of g, which is isomorphic to x. So you recover x by this symplectic reduction. Now let's look at the associativity condition for s equals to 1. And don't try to understand what it says. So it says MTR, you pick MTR and consider product with MT1, which is G times S. And then you do a symplectic reduction. Then you should get MT R minus 1. That's what it says. So let's describe this left-hand side. So maybe so in general, let's write x instead of MTR. Then consider this. So this is the level set is a triple. So the moment map for this G cross S is just a action map. So this is a moment map for G cross S. So the level set is a set with triple which satisfies this condition, and you quotient out by the action of G. And then you find that this is the same as x times G star S times G, the level set. So this goes to x is G, I think. So this is the same as x times G star S. So the statement for S equals to 1 says MT R minus 1 should be fiber product of MTR with a constant slow release. And this kind of operation, so this we did Hamiltonian reduction. So this is a special case of Hamiltonian reduction and called a constant reduction. So if you do constant reduction, you decrease the number of puncture by 1. So MTR is only I defined for non-negative R, but you view this as a definition of MTR, then you can also try to define MT0 as constant reduction of MT1, which is G cross S times S. So let's look at what it is. So this is a triple. Such that G S1 equals to S2. But there's a theorem of constant which says the following. So this is the old result of constant again. So this constant Schroderi slice is contained in so any element of constant Schroderi slice is regular. So this is an element of X whose dimension of centralizer is equal to rank of G, which consists of G. And any regular G orbit intersects S at exactly at one point. So this is a result of a constant. So this means if G S1 equals S2, and because both are elements of S1, this necessarily means that S1 equals S2, and G is a centralizer of S. So this is a set of elements. So MT0 is a set of elements in G cross S, where G is a centralizer of S. So this is what it is. And this is called a universal centralizer. And appears in representation theory quite often. And it can be understood as a spectrum of equivariant cohomology group of affine Grassmannian for the dual group by a result of Ginzburg, where G check, a group of G check is G check loop quotient out by the okay. So this looks nice. And so as I explained, MTR is a constant reduction of MTR plus 1. So in particular, this is a S scheme. And so MT0 is also a S scheme, but it also has a group scheme structure. Because you can, so the group structure of G gives the group scheme structure here. And then if you look at this group structure, use this group structure, I can explain why this family of Poisson variety must be unique. So in order to do that, you consider action of group scheme on the product of MT1 and empty R, then one can show that the function on empty R plus 1 is isomorphic to invariant part of this group scheme action. So this gives the uniqueness of MTR. Okay, so now let me explain examples. So of course, the easiest example is the case of SL2. So as I said, MT3 defines everything. So the question is, what is MT3? And you find in this case, it's just, so it has to have 3 commuting actions of SL2. And you find that it's a tensor product of 3 tensor product of C2, where so each C2 has a natural Hamiltonian action of SL2, which induces symplectic. So this is just a symplectic vector space. Symplectic vector space. And this action, natural action, induces 3 commuting action of SL2 here. So this is very simple. But then if you try to compute what is MT4, you find that this is isomorphic to minimal nilpotent orbit closure in D4. So here, minimal nilpotent orbit is non-trivial nilpotent orbit of smallest dimension, which in this case just orbit of some root vector. So why, you might ask why D4 appear, because we were considering SL2. But this you can see if you write Dynkin diagram of D4. You find here and here and here, you find the 3 commuting action of SL2. But it has to have 4 commuting action of SL2. But if you write affine Dynkin diagram, you find another action here. So this Dynkin diagram shows that this has 4 commuting action of SL2. It's not a proof at all, but I just want to convince you. But you find that this Moore-Tachikawa variety is quite non-trivial because we get singular variety. And also somehow D4 appear, although we are considering type A1 case. And let's look at the associativity condition. Associativity for equals to S or equal to 2. So this says if you do symplectic reduction of this product of symplectic vector space, then you get a minimal nilpotent oblique closure in D4, which looks quite a non-trivial statement. But it was well known for physicists as ADHM construction of minimal nilpotent oblique closure. So associativity condition in general describe this kind of a highly non-trivial isomorphism between symplectic varieties. Sorry?
The thing you just erased?
What did I erase?
This fact that there's this action such that C joint and T are plus 1.
Ah.
The end of this limit is still not correct. How do you prove that?
The,
Based on construction?
the action you find from the construction. I mean, yeah. It's just the fact that it uses, it just uses S-scheme structure. But this isomorphism is quite non-trivial. It's good, very good exercise to show this isomorphism if for R equals to 1, for example. For R equals to 1, this says you get cotangent bundle to G from G cross S, G cross S. So this kind of isomorphism, I don't think it's written in any literature.
So this is basically this property 7. This is sort of equivalent to just the construction of Ginsburg pageant.
Construction what?
The Ginsburg pageant construction.
Yeah.
This is like basically
Yeah.
the
This is
statement.
Yeah, exactly.
It's too late.
Yeah, so this is a kind of Hamiltonian reduction. I forgot how they call it. Any other question? Okay, so let's look at the case for SL3. And then MT3 already becomes non-trivial. And what we get is minimal nilpotent oblique closure in E6. And so now I think you can understand why it's E6. So if you write linking diagram for E6, you find two commuting action of SL3 here. But you find another one if you write a affine linking diagram. But you cannot continue like this forever because you go outside of linking diagram. So in general, there is no simple description of Omoata-Chikawa varieties. So although there's no simple description as a varieties, but there is conjectural algorithm to compute Hasse diagram for MTR for SL type A by Jethro. And if you look at the conjectural Hasse diagram, you find that it's completely, totally new series of symplectic varieties. So this is really something very new. There's another remark. So when type A, so in general, so this is supposed to be a Higgs branch of 4D theory, which is the same as Higgs branch of 3D theory by S1 compactification. So it's supposed to be the same as Coulomb branch of a Miller theory. And if Miller theory is a quiver gauge theory, you can describe in terms of BFN construction. And which is a case for this type A case. And MTR is the same as Coulomb branch defined by Braverman, Finkel, Nakajima, although Nakajima-san didn't explain, of the 3D gauge theory associated with, so I have to describe a quiver. So quiver is like this. So this is the star-shaped quiver with R legs. And for Coulomb branches, there's a theorem of Weeks. Which says Coulomb branch of 3D gauge theory defined by BFN have symplectic singularities. Rarities. And the symplectic singularity, this means by a Cardin theorem, in particular, by it has finitely many symplectic leaves. So this makes sense. Any questions so far? So this is a description of Higgs branches. Now I want to describe corresponding vertex algebras. So the vertex algebra correspond to class F theory is called chiral algebra of classes. So I want to consider the image of SG sigma by this map V. Actually, beam, pillars, rusty, one reads with the paper with the same title as this, gave a conjectural mathematical description of the chiral algebra of classes. So what they basically said, you can upgrade the construction I explained to the affine setting. So let's try to do it. So again, it's enough to construct a chiral algebra for genus 0 sigma. So I want to describe or construct the image of SG4 P1 with R punctures. So what I want to do, so I want to upgrade everything the vertex algebra setting in such a way that we recover the statement for Higgs branches. So this means if you have a symplectic variety, you want to find some vertex V or A with whose associated variety is isomorphic to the given variety. Of course, this is in general, this is a very difficult quantization problem, but I don't have to do it for every symplectic variety. I just want to do this for MTR. And the associativity condition used symplectic reduction. So to define symplectic reduction, we need this moment map. So I have to find analog for moment map for vertex algebra. So this is easy to guess. So this should be a vertex algebra homomorphism from affine vertex algebra for some level k to v, such that which induces so any vertex algebra homomorphism induces Poisson algebra homomorphism between C2 algebra. So it induces a morphism between associated varieties. So you have a morphism from XV to X of VKG, which is the same as G star, as I explained in the first lecture. So this should be the same as this momentum. So this should be condition. So next, what should be the analog for this symplectic reduction? As I said in the beginning of today's lecture, so symplectic reduction can be described by the classical BRST reduction, although I don't explain what it is. You can upgrade this BRST cohomology to the BRST cohomology of corresponding vertex algebra. And you find that it's the same as so-called relative semi-infinite cohomology. This is a special case of BRST cohomology. And you find, so this is a right thing to do, because if you compute corresponding, so because this is BRST, if V1 and V2 are VOA, this is also vertex operator algebra. So you can take corresponding associated variety, and you can show that this is the same as symplectic reduction. In not always, but nice cases. So this operation recovers this symplectic reduction. This is, yeah. So this should be the right thing to do, but there is one constraint. To this relative semi-infinite cohomology to be defined, to be defined for to be defined, we need one condition that the level of V1 and the level of V2 should be twice of dual Coxeter number if G is simple. So otherwise, if this condition is not satisfied, you cannot construct BRST operator. So we need this condition, and we are assuming that the V1 and V2 are in the same level. So this means the level of Vi are all minus H, which is critical level. So I have to work at a critical level. So this K has to be a critical level. But it's okay. We can always work at critical level. So I think the problem became clearer. So we want to construct a family of vertex operator algebras which has vertex, which is equipped with vertex algebra homomorphism. So more Tachika variety has R commuting, MTR has R commuting action of G. So its upgrade to the VOA should have R commuting action of affine Katsumudi. So we need to have vertex algebra homomorphism from R tensor product of affine Katsumudi vertex algebra to VR. And also, this relative semi-infinite cohomology satisfies the associativity condition. And associated variety for V2 should be cotangent bounded to G, and associated variety for V1 should be G crosses. That's what we want to do, but maybe I do it tomorrow. Okay.
So, do you have any questions?
It's strange if this level is different. So I don't know how to make things compatible if you choose different level here. Have to be total level should be, I don't know, yeah.
More questions? Okay, so let's thanks the speaker again.